Good morning. Let's start. So the last thing we did last week, I showed you some example that you can improve accuracy by averaging on sensors, and we talked about shaft encoders, and I showed you actually two examples where we can improve things by averaging. One example was how to correct the main error of a rotary encoder, which is a runout, by instead of reading just at one read station, instead of reading just here, and the eccentricity will affect the radius and affect the angular measurement, to read on two opposing stations and average them. Now this is not differential, this is just averaging two stations together. Okay, each reader can be differential if you like to, but this is just averaging two stations together. Okay, so it will look like this. And now when the eccentricity makes this maximum radius, this will be minimum radius. So the example I gave, if this is r plus delta, this is r minus delta, if you add them together, the delta cancels out. And I also mentioned if you just go behind this wall, on the other side of this wall there is a display cabinet of all the instruments, and you can see there the first rotary encoder in the world which uses that, and that is theodolite, which is of course used for surveying. And actually this one in the glass case across the wall is so old, it looks like at least 100 years old, that the averaging is done by the user. It has two eyepieces. When you look at the theodolite across the wall, it has two eyepieces, so the user actually takes a reading from here, a reading from here, and manually averages them together. Like, of course, in the more modern theodolites, this image was superimposed on this image, so the averaging is automatic, and the electronic theodolite is just two electronic readouts which are connected like this. But the principle of averaging to cancel the error, as you can see, is 100 years old. Second example I gave you, that you can actually improve the whole encoder by, instead of taking a disk and putting a readout station, you can take two disks, putting them together, and then the whole disk will be modulated. And just to remind you, I showed you two disks. I wouldn't even bother with that. I show you two disks, and then you put them together and you turn it, the whole thing goes, if it's center, the whole thing goes black or white. Okay? And now you're averaging all the lines, and a disk like this typically has between 1,000 and 10,000 lines. So if a disk had 10,000 lines, okay, of those, and you took two disks together and you averaged, and the errors were random, as you recall in statistics, if the error is random and you take n measurements and average them, the accuracy will improve square root of n, assuming they're random. So this will improve the accuracy square root of 10k, which will be about 100x improvement, which is a lot. And I also mentioned that this idea is the basis of the most accurate angle standards in the world, which instead of encoders use two phase gears. So there are two gears meshed like this, and you move them out and remesh them and remesh them. Typically the gears have 360 teeth, so when you mesh them again and again and again, they average all the teeth. And using this method, either in an encoder or in meshing disks, you can get to 1/10 of an arc-second accuracy, which is a very, very small number if you start thinking what it means. Okay? So that will be 0.5 of a microradian. So it means roughly that if you have a beam 1 kilometer long, and somebody puts a business card under the end of the beam at 1 kilometer, you can detect that it tilted. Just to give you an idea what 1/10 arc-second means. Right? If there's a calculation, because half a microradian is half a millimeter per kilometer. Okay? And the other thing I mentioned, somebody here asked a very good question. So how do you make the first disk? You know, how do you have to have some master for which to copy all these disks, but how can you make a very good master? And I mentioned that some things in metrology is the art of precision measurements, some things in metrology are self-calibrating or self-checking. And I gave the example how Ramsden did the first sextant, which is also across the wall here, and it's worth your while to have a look what it looks like. So the way he did it, he took microscopes and aligned them in such a way that that each position of the wheel, the microscope had to stay aligned, and then he corrected the teeth of the gear by filing or by lapping until the microscopes always lined up with the lines, and therefore, again, what he did, if this was the wheel, he put microscope at random positions which aligned. So you have 3 microscopes at random positions. And now, if you rotate the wheel, if it's perfect, if one microscope lines up, the other 2 will line up. If it's not, you have to file the gears until eventually, at any position, the microscope will line up. And using this and 6 months of patience, he achieved better than 1 arc second 200 years ago. Okay? So, that's just all of this we went through, it's just a refresher. So now let's move on. That principle of averaging is very, very important in precision measurements. This was just one example, but it shows up everywhere. And it also shows up in the next subject. We want to talk briefly about using cameras instead of sensors. I mentioned that if you look at a book even 10 years old about sensors, it talks about all kinds of ways to measure, say, XY position with maybe optical, maybe electromechanical. But even 10 years ago, nobody would think, why don't we just put a webcam and some software? Because the cameras were expensive, and some of them were also large, you couldn't fit them in. But today, a camera module costs less than an LVDT, costs less than any sensor because of phones. So and I also mentioned, just for reference, the volume price of camera modules for smartphones. This includes the lens, the chip, the processing, everything is $1. The volume. But even the small quantity price is $10, $5. So you really can't beat it. If you can solve the sensing problem with a camera, you can't really beat it because it's a 2D sensor in one, and you can do a lot more things with it besides sensing. For example, the software can recognize the target, can recognize what's going on, and you can add a lot more smarts than you can add to a normal sensor. So the classic thing to use, so let's just think about a few basic things to using a camera as a sensor. So the camera is a grid of sensors. The old cameras were CCD, charge coupled devices. There's a lot of cameras now which are CMOS, which is an easier thing to fabricate, and it's also compatible with the processing. So you can fabricate on one wafer the camera and all the processing electronics. But this really doesn't matter. That's for electronics engineers. But what matters to you is that's an array, typically 1K by 1K, and the simplest way to use cameras as sensors is ignore the grayscale. Use them as binary, because otherwise you have a lot of data, because this gives you 1 million entries, and if you use the binary, it gives you 10 million bits of information. It's a bit too much. So typically when you use the sensor, you just have what's called early quantization. Early quantization means that when the signal comes off the camera, you immediately run it through a comparator and say it's a 1 or a 0. Okay, so I want to track a laser pointer on the wall, or a tip on the robot, or a tip of a crane using a camera. So let's say I have a crane, a building crane, which I want to track exactly the tip of the crane to 1 meter. Okay, so I put an LED at the tip of the crane, and then I see the image of the LED here. Okay, and then I track it simply by looking at which row and which column it is, if it's a 2D sensor. So the first question is, should I aim for the smallest, sharpest spot, or maybe it's better to have a bigger spot on the camera, even if it's a bit blurred? So, by now you should know the answer. Big. And why is that? Pardon? averaging, because again, if you have a small sharp spot, one speck of dust on the camera, which can happen, very common, will give you a huge error, and all kinds of other things. But in a camera, it's even more important to use a big spot, because if you use a small spot, and we talked about early quantization, you can only have a resolution equal to the number of rows or the number of columns, right? Because the way, if you use a small spot and the spot is moving, let's say spot is moving in X direction, you will get the following readout. And the first time you'll get a readout like this, and you'll quantize it. You'll make it a 1. If the spot moves, the second readout, you will get a thing, maybe in the middle, you'll get something like this when it hits 2 cells, and then it wouldn't reach the threshold because it will be too wide and low, and then it will move to the next cell, and you'll quantize it. So you will only, if you convert it to binary early quantization, you'll only be able to have 1,000 positions, okay? But if you have a big spot, you will average all these pixels which changed, and then you will have a lot more positions, because basically this pixel will change and this pixel will change, and then your resolution could be up to 1 million positions. So let me explain in an example how this is done. Imagine that instead of this round spot, which is a bit confusing, imagine that you have half the camera lit and the other half not lit, but the edge is diagonal. So imagine you have a diagonal line. This half of the camera is in the dark, this half is lit, and you start moving the line, okay? So during 1 pixel movement, a whole column, which is 1,000 pixels, will change states. So you started the movement when this being a 1, this being a 1, and let's say this is already 0, 0, 0, 0, because you are quantizing, and if it's less than half, you call it a 0, okay? Now, when you move it 1,000th of a pixel, the pixel which is just on the boundary between 1 and 0 will switch to a 1. When you move it 2,000th of a pixel, the next pixel will switch to a 1. When you move it at 1 pixel, basically all the pixels will change, because now the line will be here, and all the pixels will have changed. So now if you have a diagonal line which is 1 pixel, and this gives you 1,000 steps instead of 1 step. Okay? Now, is that clear to everybody? So as the idea, now the way I drew it here, it's not so good to measure up and down, but let's say, take an example. If you had the camera and you had a diagonal line like this at 45 degrees, and this is a grid of the camera. Okay? So this is all dark. Now, if you have this, if it moves up and down, okay, you have not quite 1,000, but if you calculate 700 pixel resolution per pixel, and if you move this way, you have it as well. Okay? So now you can extrapolate or interpolate to a much smaller change than 1 pixel, because the slightest change will switch a whole bunch of pixels from 1 to 0. Okay? Now, and then if you think about this, you realize it can stay a circle, because when it stays a circle, like we started from, when it stays, you don't need a diagonal line or anything. When it stays a circle, and when the circle moves, a whole bunch of pixels will change at this side, a whole bunch of pixels will change at this side. If it moves up and down, the same will happen here and here. So a circle is just as good as this. Some pixels will be less effective, like these pixels here will be less effective if it moves this way, but you have a lot of other pixels. So if you have a circle which is maybe 250,000 or 500,000 pixels out of 1 million, any movement of 1 pixel will cause thousands and thousands of pixels to change states. So dust wouldn't matter, and you get very, very high accuracy from the slightest movement. Okay? Yes, please.
Well, what about rotational movement?
There's no problem to do it. You just need a target which is not rotationally symmetric. Because imagine if you had a camera and you projected a square, okay, Projected a square, of course, you can analyze how much this end moves, how much this end moves, and you'll have rotation. And you realize right away that you can tailor this pattern to what you want to move to make the largest number of pixels change when the change you're interested in occurs. So if I wanted rotational movement, what I would do, I would actually do something else. I would maybe make a pattern which looks like this. A bunch of vertical lines. So ideally I would make like a few hundred lines. So when it turns, there's a whole bunch of pixels changing along each line, and so altogether I get the maximum number of pixels changing. Okay? So the target, now this pattern is not so good for up and down movement. Okay? Let's say a square is good for everything. It's good for this, it's good for this. Okay? And if you look at it, I can do even better than a square. If you think of it, theoretically probably the best thing would be a hollow square frame. Because then I also have pixels on the inside changing, not just the, okay? So anyway, for each type of movement, you can think through what is the best pattern. Usually it doesn't really matter because you have enough sensitivity here, okay, even from a simple pattern, because this pattern may be difficult to generate unless you have a target in this shape. You can always have a target illuminated with an LED in this shape far away, and you look at this image. Okay, this also has the advantage that it's distinct, so you can't confuse it with some street light or with something else around. So if you look at a crane to know where the tip is, and the crane has some headlights on top, this is a bit dangerous because a camera can pick up some lamp and think it's a target. But if you use this as a target, it's hard to believe there'll be an object lit in the form of a square on the tip of a crane. So you can see that the same camera will measure x, y, theta, and all what you need is a second camera from the side, and it will measure, say, y, z, and phi. So you get a 6-degree of freedom sensor with two cameras. Okay? There's actually some student here in MEC who did a project where you can do it with one camera, because the camera is color and you don't really need color. So you can illuminate a target with red and blue and green LEDs and look at each image separately. So you have like 3 cameras in one. So if you're clever enough, you can do it in one camera. If not, you do 2 cameras. So it's a very, very versatile device, because first you can measure 6 degrees of freedom if you want to, and there is other ways to measure 6 degrees of freedom. There's many tricks you can do. It's a very versatile device, very low cost, and the same camera can still be used as a camera. It can look at the scene, detect if there's some problem, can be used as monitoring camera. Okay? So besides being a detector, it's still a camera useful for other things. For example, you have a camera just monitoring for safety, what the crane is doing. The same camera can give you position feedback. Now, cameras have one disadvantage over the split detector sensors we discussed before, and can somebody maybe guess? So far it looks like a camera is the best sensor because it does everything, but in terms of rejection of noise, there is still an advantage to the split detector over a camera. Can somebody think of it? Yes, please?
Distortion?
Correct, although the lens of the camera has a slight distortion. The camera itself doesn't, because it's made on a lithographic machine. It's deadly accurate, but the lens. But the distortion of lenses is very small. Like, it's easy to get a lens which is 0.1% or even 0.01% distortion. Okay, and B, it's always the same, so you can take it out with a lookup table. You can look at a grid, calibrate the distortion with a lookup table, and you always multiply by this lookup table. So it's very easy to fix. Distortion is one of the easiest things to fix because it needs a very small lookup table, because distortion is always a low order function. It's like parabolic or square, so you just need like 3-4 points and you can correct the distortion. But remember, the weak point of all optical sensors is stray light and noise in the form of light. Okay? So what advantage could a split detector have over a camera when it comes to that?
Differential?
Say it again?
Differential?
Okay, first of all, differential. Split detector is truly differential. The camera is not differential. And that's a problem. I mean, you can in some way do it differential. You can take a camera which looks at a sensor, and then you can take another camera to look at the sensor, but you just use an average. So it's basically, you take the difference between the cameras. One camera just looks at the scene to measure the light, but it's not so good as differential. So, but there's even a much more important disadvantage of a camera versus split detector. There is some very clever trick we said is a must-do with optical sensors, and it's hard to do with a camera. Besides differential, what else did we do with an optical sensor to be immune, say, to the light in this room?
Filter.
Well, you can do this in a camera too. You can put a filter in front of a camera. Although color cameras have their own filters, so you can only filter within the visible. But something else. We said the best way to get rid of noise is not to use a DC or what's called a CW, continuous wave light source, but modulate the light source. Because then you can pick a very high frequency which doesn't exist in the room, say 100 kilohertz. And we went through several times with this calculation that you can put a bandpass filter after the sensor, so it only sees light modulated at 100 kilohertz, way above the flicker of fluorescent, way above moving objects. And that is the most effective way to eliminate noise in optical sensors. But why is it difficult to do in a camera? Yes?
Your frame rate will pick up the flicker?
Of course, because a camera is a sampled device. You don't get a continuous signal. The camera looks at the whole frame and dumps it out, and then looks again at the whole frame and dumps it out. So a camera is the same as an A to D with a certain sampling rate. Is there anybody here who doesn't know what the sampling rate of an A to D is? Anybody who doesn't know that? Okay. So we are going to cover it next month. I wouldn't get into it now. But when you have an A to D, it doesn't really continuously digitize a signal. It captures a snapshot in time, digitizes. It captures and digitizes. So if this capture rate, which is called the sampling rate, is too slow, it's not aware of changes between the samples. So a camera is a sampling system with a very low sample rate. What is the sample rate of a camera? 30, because most of these cameras, when the video cameras and all these cameras, they take 30 frames a second. Some take 60, you can buy some which take 100, but standard frame rate, like television, was actually 30 frames a second. It's 60 frames, but one frame was even lines, one frame is odd lines, so it's interlaced. So the net effect is 30. And why was 30? Why are cameras at 30 frames and not at 5 frames?
That the eye needs?
Exactly, because to see continuous motion, smooth motion, you need about 25 frames per second. So they just made the cameras to sample a little bit faster than what the eye needs, because the eye is even a slower filter. So the moment the camera captures 30 frames a second, it looks continuous motion. Okay? So nobody builds cameras which are faster because the eye wouldn't see the difference. But for a sensor, it's very bad, because if a camera samples at 30 frames per second, which is the same as 30 hertz, because of the Nyquist rate, it means it can only pass information at 15 hertz. Because if you have a sine wave, we went through that already several times, you have a sine wave, and that sine wave is 15 hertz, you have to sample it at least twice per cycle to recover it. That's what's called sampling theory. And therefore, a camera which is 30 hertz, its bandwidth is only 15 hertz, and 15 hertz is very bad because there's lots of things in the room which change at the rate of 15 hertz. Anybody moving, shadows, projectors, light changes. So it's way too low a rate to do optical filtering because it's the same rate as the information. And unless you have very slow moving target, and by software you can filter it. Let's say if you're following a crane and you know the crane can only move a meter a second, so what the software does, it averages many frames to get rid of noise. But the camera itself, if you modulate the light at, say, even at 50 Hertz, the camera will give you garbage. It's like what you get when you try to photograph with a camera a TV screen. You get some half the screen, or a computer screen. You get sometimes half the screen in the picture because of insufficiently high sample rate. So the weak side of the cameras is the very low sample rate. It's not suitable to sense high-speed motion. It's basically not suitable to sense anything with information contents of more than 15 Hertz. And even 15 Hertz is a limit. So let's say 10 Hertz. While a sensor which has a split detector and a light modulated at 100 kilohertz can easily pick up vibration of a few kilohertz and track it. Good. So that's a trade-off, but otherwise the camera is a very good sensor. Yes, please.
Could you use multiple cameras to phase shift it to capture?
Yes, but then they have to be registered to one another. You can always do some parallel shifting because you can control the sample point in a camera by the trigger. So you can have 10 cameras, each one at 15 Hertz bandwidth, but each one shifted a tenth of a cycle. And then you will get 10 times the bandwidth, but it's still only 150 Hertz. And you have to register the 10 cameras so the images align. Otherwise, when you jump from camera to camera, it appears the object is jumping. So it's problematic. Can be done, but it's not worth it. You can buy special cameras, high frame rate cameras. And you can also buy linear CCDs, which are much, much faster. Like you can buy if you just want to measure movement in one axis, you can buy linear CCDs, which have 1,000 pixels, okay, say 1K, and these can have a frame rate of 100 kilohertz. They are specially designed for motion sensing, and they are very, very fast. Okay, and they actually have multiple taps, so you can get the data out fast enough. Otherwise, there will be a bottleneck to get all the bits out. So you get multiple taps, so you get the data out in semi-parallel. Every 100 pixels, you have an output. And these are standard devices. You can buy those. And that's basically how you do it. If you have to measure with the camera things which are much faster. Okay, so that's sensing with cameras. We talked about sensing with detectors, sensing with encoders. So I think that is as much time as we have in this course to talk about optical sensors, but certainly that's the direction more and more sensing goes. The leading company who started introducing very good optical sensors is a Japanese company called Keyence. Now everybody makes them, but they were one of the first companies who realized that instead of making a dial gauge or a mechanical indicator, you can do it optically. And they started selling very nice little optical sensors, and now everybody is doing it. Okay, so now any questions about these ones, which I would call classic optical sensors? Classic because they all operate based on geometric optics. They don't operate on interference, they don't operate on wave principles, they operate on classic geometry. Any questions about those? Yes?
So what is the fastest you can get as a camera?
Okay, so I'm not sure I'm up to date, but linear cameras you can certainly get with a 100 kilohertz rate, because I've used them at this rate, so I know you can, even years ago you could get them at this rate, and I can do a quick estimate because you can make a simple array, a fully parallel array, as a custom chip. Okay, let's say if you want to build a custom chip which has 100 by 100 sensors, So it's 10,000 sensors, and you want to bring each one out with its own amplifier. Okay? So this will operate at the same speed as a single detector. So in commercial chips, I would say that's the limit for linear, and maybe 1,000 hertz is the limit for arrays in commercial chips. But if you have some special application where you really need a 2D sensor camera and you're willing to make a custom chip, you can do this with a parallel processor. Custom chips are not that expensive today. Maybe it will cost you $50,000, but for a product, it's still worth it. And then you can make a array processor connected to a camera which each pixel is brought out. Because in the silicon, 10,000 wires are not a problem. If you had to bring it out with a connector with 10,000 pins, it wouldn't work. But if it's all one silicon chip, and these are brought out on the silicon chip to the amplifiers, and then you have an array processor, and it's all on one chip, that's very doable. Matter of fact, we have done things like this in the past. When we needed for projects a super fast sensor, we made a custom chip like that. And then you can get actually a camera where the sampling rate, or the frames per second, is in the order of 10-20 million. Because it'll be as fast as a single detector. And then you start asking a question, how fast can a single detector be? So a normal silicon detector, if you don't do any tricks, is 1 megahertz. If you start doing some tricks, like a pin detector, you can go to a gigahertz. How do I know that? Look at fiber optics. All of fiber optics, the detector goes to many gigahertz. So there's really no limit if you're making custom chip. But you can go to specialty materials, gallium arsenide, pin detectors, you can do many gigahertz. But as commercial chips, these are good numbers to keep in mind. 100 kilohertz for linear, 15 hertz for standard webcams, and maybe up to a kilohertz for specialty high-speed cameras. The biggest problem is getting the data out, right? If somebody gave you a camera which works at, say, 10 kilohertz, you wouldn't be able to handle the data, because each dump is a megabyte or a megabit. So if you had 10 kilohertz times a megabit is 10 gigabit. How can you process 10 gigabit? So the limit wouldn't be the camera. You wouldn't have a device except for a parallel processor which knows what to do with so much data. Okay? Because even a regular camera like this gives you 30 times this is 30 megabit per second. Even if you do early quantization, you just look at it as binary, you get 30 megabit per second, which is already a heavy load on the processor. Because the algorithms have to run in real time, right? So it has to process in real time and track and average and everything 30 megabits per second. So the limit is also the processing power. But in a custom chip, you can do anything. Okay, so now let's move from geometric sensors to sensors based on wave theory of light, which is basically interferometers and all kinds of ideas like this. So I suspect a very quick refresher is needed in optics, as usual. So if you look at light as waves, not just as straight lines, the first thing you notice is a phenomena called interference, because the waves have a phase, and if you can have two waves which reach a point. If you have a point, if you have two waves reaching it, if the two waves arrive at a point in phase, they will add up together and you'll get double the amplitude. But if the second wave comes in antiphase, you can actually get dark here. Although it's basically you can shine with two lasers on a spot, and at this spot you'll get dark, although both lasers hit. Okay, now in real life it's hard to demonstrate that, because the lasers have to be phase locked together. But it's easier to demonstrate if you take one laser and split the beam into two. So say if you take one laser, okay, split the beam. This is a beam, so you put let's say you put a beam splitter, so now you get two beams coming out, and then you take these two beams, and you have two mirrors here, and now these two beams come together. Now they're exactly in phase. Okay, they're exactly in phase because everything is symmetric. So these two beams will add up together to the same beam as here. But if you change this distance a bit, just by quarter wavelengths, this beam will be half a wavelength out. And if it's half a wavelength out, these two beams will hit together and interfere, and in spite of two bright beams coming together, actually here it will be dark. Okay? So somebody very clever understood that in the year 1900, okay? Before lasers, there were no lasers, but you could do this experiment with some other light sources, like some special arc lamps and special lamps with many filters. You can build up a beam which is monochromatic enough. Monochromatic meaning one frequency, one color. So you can, even before lasers, you can build up a beam with a sodium lamp or some special sources which is monochromatic enough that you can do this experiment, that when you move this mirror a little bit you can get either light or dark. So somebody very clever in 1900 thought of that and said, hey, that's a very good position sensor, because if I just move it a little bit, half a wavelength, which is like 200 nanometer or 300 nanometer, it'll go from full light to full dark. If I move it a bit more, it'll go light again, then dark again. So I can measure this movement just by counting fringes. And I can do a quadrature trick, just like an encoder, with two sensors at 90 degrees, so I'll know the direction. So this is really an encoder. But when I move this, instead of actual lines, I'm using the wavelengths of light as lines. That has huge advantages, because the wavelength of light is stable, you can make a long encoder, it's very fine. It's very difficult to scribe lines as dense as the wavelengths of light. So that is a perfect encoder. If I can move that, okay, I can measure very small movements to great precision, and that's called an interferometer. Okay, this whole device is actually a position sensor. If you connect this to a slide, you move it and you count here with a photosensor. You put a photosensor, you move this mirror and you count how many times it goes light or dark, light or dark. You actually have an encoder, and this whole thing is called an interferometer. And this is a key instrument in measuring very precise measurements in many fields. Okay, the classic interferometer sometimes is drawn differently. Sometimes it's drawn like this. You take the laser and you put a beam splitter here. Okay, you put a beam splitter. A beam splitter is a mirror which is half silvered. So it's a 50% mirror, so what happens? Some of the beam goes like this, and some of the beam is reflected. Okay, 50-50. So that's 100% of the light. Here you get 50%, here you get 50%. Now, you put a fixed mirror here, so this beam will return to here. Some of the beam will be reflected back to the laser, but we don't care. So this is the laser. This is a beam splitter. So one beam will hit the mirror, come back here and go back this way. This beam will go here, and then you put another mirror. Now this beam will also hit the mirror. Some will go back to the laser that you don't care, and the other part will end up here. So you'll end up with the same situation as here. When you start with the wavelengths of light, here you'll end up with one wavelength, and here will come with another wavelength. If these distances were exactly the same, they will add up together. You'll have a bright light. If you start moving this mirror, if you move this mirror lambda over 4, the light will shift lambda over 2 because it's double pass. If you move this lambda over 4, the light has to go lambda over 4 more and return lambda over 4 more, so lambda over 2, so you get this situation. Okay, so this is exactly this. Sometimes this is more convenient, sometimes this is more convenient. So, who is the person who invented this clever idea, and why did he invent it? Another hint, he was the first American to get the Nobel Prize for this.
Is it Michelson?
Right, very good. So how come the rest didn't know, that they were just too shy to speak? So this was Abraham Michelson, the first US physicist to get Nobel Prize, I believe around 1910, something like this. He got Nobel Prize. And so why did he need such an accurate interferometer? Remember, before lasers, before anybody even worked to such accurate measurements.
We wanted to see if there was an ether to measure the speed.
Ah, okay. And what is the ether?
The reference frame, which is absolute, which the speed of light would change another reference frame compared to that. Like a medium, I guess.
A medium. Okay, so so it turns out the ether is something that everybody wanted to measure until they discovered it doesn't exist. Okay, it was believed in the late 19th century that the whole universe is filled with a mysterious fluid called ether, because people couldn't understand how, say, sunlight reaches from the sun to the earth. They knew sound waves can propagate because they move the air. You have air pressure variations. You could see waves in the ocean, they move the water. And they knew the sunlight or light is waves, but they said, how can these waves travel through nothing? So there must be something which has no mass, no physical properties, but it conducts waves. And that's ether. The word, when you say in English ethereal, it still means something with no physical properties, like you say it about a person sometimes. So the word comes from the ether. So ether was this miraculous fluid which fills the universe, which allowed waves to propagate. Okay? So then Michelson, when he thought about the interferometer, he was actually interested in measuring the speed in which the earth moves through the ether. Because he said, if there is such a thing as ether, if you can, the speed of light, if you are on the earth, and the whole thing is full of ether, okay? The earth is rotating, and the earth is also moving around the sun. So if you measure the speed of light this way, and you measure the speed of light this way, you'll get two different results, because here there's a Doppler shift. At least if you measure the frequency of light. Because if the object moves, like the measuring equipment moves against the light, you'll get a Doppler shift. But across, you'll not get a Doppler shift. So Michelson said, hey, that's an excellent device to measure speed of light in two directions. Okay? Because he originally did this to measure the speed of light in the ether, to detect the speed we travel through the ether. So if we travel through the ether this way, this wave will be affected by Doppler. It will be shrunk, let's say, but the cross wave will not be affected by the movement through the ether at all. So then you'll start getting here changes. Right? You'll get a dark or a light fringe, depending how you orient this device relative to the ether. Okay, anyway, it was a beautiful theory. It turns out there's no ether, so it didn't show anything. When he built it on top of Mount Palomar and very carefully adjusted it, he detected no difference which way you aligned it. So he realized there's no ether. But in building this device, he had a lot of trouble, because it wasn't simple to build this device, and then he realized how sensitive it is. Now, I'm not sure what came first. I'm not sure if he thought of this first as a measuring device and then wanted to measure the ether, or thought first of measuring the ether and then thought of this as a measuring device. But it was about the same time. It's not that it's not known, it's just that I don't know it, but you can look it up. So anyway, so he realized that this is a very, very good measuring instrument, and he got interested in metrology, into standards. Say if you have all kinds of standard bars, you want to compare them, standard meter, standard yard. So he started applying that for very precise measurements, because not only does it switch from dark to light with a quarter of a wavelength of light, you can interpolate between, right? So if quarter of wavelength of light, typically this is done today with red light. Today this is typically done with 633 nanometer, because that's a wavelength of the helium neon laser. You need a very stable laser. So quarter wavelengths of that, okay, is about, let's say, 160, okay, roughly. So 160 nanometer will change you from light to dark. But you can interpolate. In the meantime, we get brighter, brighter, darker, darker. So you can interpolate to lambda over 100 easily. So lambda over 100 is 6 nanometers. Most of the high-end interferometers today read out to 1 nanometer. So it's a very, very sensitive device. And you can do all kinds of differential tricks here. You can do a whole slew of tricks. Because actually what happens, if the thing is not perfectly aligned, on the same target, you wouldn't see all black or all white. If you actually look at the target, because of imperfect alignment, you will see bands which look like this. Because in all the areas where the path difference will end up to lambda over 2, you'll get dark. In all other areas you get light, but since nothing is so perfectly aligned, it wouldn't change all at once from light to dark. This will change, and you will see like a pattern shifting. And that actually is an advantage. You can align an interferometer to go all light, all dark, but this is actually an advantage because it has a moire effect. And you can put several detectors, you can do all kinds of tricks. Today it's analyzed, by the way, with a CCD camera. The modern interferometers, they just look at this pattern with the camera, because then the software can deduce from that a lot of things, much more than the detector. Because interferometer, you're not interested in very fast measurements, so camera has enough time. So most modern interferometers actually don't put it through a split detector, but put it straight onto a CCD sensor. And you analyze it with software. And those ones can go to a nanometer. Because imagine if this is a full movement is 150 nanometer, camera can easily analyze 1% of that. Okay, so out of this whole idea of ether and all kinds of other ideas which turned out to be a mistake, something very good came out, which is an interferometer, which is the base sensor for very precise measurements, both linear, also rotation. You can build it also that it measures rotation, also measures tilt. Right? If this would tilt, then this whole band pattern will shift. And you can have two, so you can see if they shift together, it's motion. If one shifts and the other shifts the other way, it's tilt. So by using all these clever differential tricks, you can measure tilt, you can measure motion. So this is today the standard of accurate displacement measurements, especially when you need to measure it over a big range, because a capacitive sensor is even more sensitive than this, but only works well, say, up to 1 millimeter. But this works well up to, say, a few meters. The limit to the accuracy, of course, it goes through air, and the air itself is not stable. Because if the speed of light in air changes, the readings will change. Now the air has moisture, has CO2, so it's constantly changing speed of light. So that's a problem. The way they deal with it, first of all, this is differential by nature, because this and this both go through air. Right? So it's differential by nature because you are comparing these two. And there are many other tricks. To do absolute measurements, you put this part in vacuum, and then you compensate for the air. And anyway, I wouldn't get into that. But it's a very good instrument to measure from, say, 1 millimeter to 1 meter, because below 1 millimeter there are simpler ways to do it, like a capacitive sensor or an optical sensor. But between 1 millimeter and 1 meter or several meters, that's really one of the best instruments. It's expensive. Typically, an interferometer, unless you build it yourself, costs many, many thousands. And another problem, you can't make it small because it needs a laser, and it needs a gas laser, to a very stable laser, so it's big. Like a helium neon laser, this big, so you can make a teeny sensor out of it. But there is a trick how to do this with an LED without a laser. And that's the next thing I'm going to explain. So, does everybody understand how this interferometer is called? And this is still called today a Michelson-Morley interferometer, based on the Michelson experiment to measure the ether. Okay, so everybody understands how this works? Good. Okay, we move on. Usually interferometers are used to calibrate other position sensors. Very few people really need this accuracy and have this much space and money to build it into equipment. So say if you have a CNC machine tool, it doesn't use an interferometer, but when you build it, you put an interferometer on it to calibrate it. And after that, you just rely on its own encoders. So they use the interferometer to generate the lookup tables. So this idea worked from starting 1900 till today, but there was no other idea of that sensitivity and that capability until somebody clever noticed something which for some reason took a long time before people started using. So to explain the other idea, let me show you first what a grating is. So when you take a grating, which is like a regular pattern of lines, so let's say I have a grating, and the grating is just a regular pattern of lines, and let's say the line spacing, let's call the line spacing D, and let's look at it from the side. So you have lines, and the spacing is D. When you shine a laser through it and you look at a screen, some of the laser will go straight through. The laser beam is much bigger than the lines, right? I'm showing the lines exaggerated. The lines are very fine pitched. So these are the lines. When I shine a laser, it will go through, but something else will happen, and what will happen? What will I see on the screen? Speak up.
Pattern. The image also goes outwards.
Yeah, basically, typically I will see two more spots. The main pattern I'll see is the same laser beam. Not only will give it a spot here, it will give me also two more spots here, and these are called the diffraction spots. What I'll see is diffraction. Okay, and you all know that, you learned it. If not, please look it up in Wikipedia or somewhere, diffraction theory. And this angle alpha, if this is D and the wavelength here is lambda, what will be this angle? You learned it in Physics 101. Every one of you passed the test on that. I'm serious. So, what's this angle?
2 sine theta.
Pardon? What is it? Come on, fellows. Listen, it doesn't matter how many years you spent in university. The only thing which matters is what you remember after university. So think about
2d sine theta.
Is that what?
2d sine theta. Sorry.
No. What's the angle? Ask what's the angle.
Oh, that.
What is alpha? But you are getting there. Anyway, so it turns out, you can prove in a few seconds, that alpha is let's just see it. It's lambda over D. Okay. Now it's actually sine alpha. Sine alpha is lambda over D, but for small angles, the sine of the angle and the angle is the same. And the way you prove it, all what you do is you say like this: at this distance, let's call this distance x. Okay. Now, if I go like this distance is, if this angle is alpha, okay, I can calculate this distance, and all what I have to calculate is at what angle will the path difference equal lambda. Because the path difference equals lambda, I will get constructive interference again. So if you want to do the calculation, you just look at two slits. You just look at two slits distance d, and you say, okay, if I have a point here, these two distances are equal, so clearly I'll get a bright spot here. Okay? Okay, now at what any other angle will I get a bright spot? So let's take another angle, and now these two lines, okay, at what angle will the path difference between the two be equal again to the wavelengths of light? So that's a very simple problem. I can do this. Okay? So this angle, alpha, okay, is equal, this angle is equal this angle, alpha. Okay? So the path difference, if this is d, okay, if this is d, this little thing, which is a path difference, is d sine alpha. Okay? Right? Because this or this sine alpha. So d sine alpha has to be equal lambda in order to get the path difference one wave. So because of this, sine alpha is lambda over d, and for small angles it also equals alpha. So it's as simple as that. It just takes 5 seconds to derive the equation for a diffraction grating. But you should remember that. So if you ever forget the answer, you can rederive it. Okay. So, and the same will happen if it happens in this direction. It will also happen in the symmetric direction. So this is the axis. So if it happens in this direction alpha, there will be another direction symmetric where it also will happen, right? Just from symmetry argument. So because of that, if you have a grating and you send a laser beam through it, you'll have two spots besides the main spot which will be bright. Now, then you can say, hold it, wouldn't there be another angle, much bigger angle, where it will also end up with a right interference? Yes, there will be many angles. So actually there will be, this is called first order, but there will be second order, third order, but they'll get weaker and weaker. So for most gratings you just see 3 spots and then you get a weaker spot here. Okay, so this is diffraction, this is called the first order, this is called the zero order. So this beam is called the zero order, and this is called the first order, and so on. For greater confusion, some books call this a first order and this a second order, but most books call this a zero order and this is a first order. Just don't be surprised if you see differently. So this is, so far you don't understand why I'm telling you all that, but you'll see in a minute, because that can be the basis of a very useful sensor. So, is that clear how diffraction grating works? Okay. So here is a diffraction grating. Now the same thing works in reflection. This is a transmission grating. Exactly the same thing works if I reflected the laser. If I reflect the laser, the reflections will come back into 3 positions. One reflection come back straight, one will come here, one will come here. So if this is a diffraction grating, and this laser unfortunately is much weaker than my usual one, but I think you can see the spot. When I hit it on the grating, and then you see 3 spots. I think you can't see that, so I'll turn off the light for a moment. Now you may be able to see it. So this is a laser spot, but if I bounce it off from the grating, you see 3, can everybody see 3 spots? Okay, so this is a 3 spots. You don't see the 4th and the 5th because they're too weak. Okay. Now, so it's clear if I change the wavelengths, this angle will change. But what is not clear to people is what happens if I move the grating. If I take this picture and I move the grating up and down, does it make any difference or not? So I try this. Okay, I do that. I put the grating here. Again, I look at the reflection. I see here there's 3 spots. I move the grating sideways, up and down. My hand isn't stable enough, but basically nothing happens. So on first look, when I have a grating in a laser beam, both the derivation of the formula and also the experiment says if I move the grating this way or this way, nothing happens. But it turns out something very important happens if you could see the waves. Here I don't see the waves, but if you can really see the waves, like waves on a pool, and if I move the grating, something very important would happen. So this I didn't expect you to know, but maybe there's somebody here who is good in physics. So what happens when you move the grating to the light? Obviously the amplitude doesn't change and the angle doesn't change, because the theory and what you saw, the demo, the angle didn't change when I moved the grating. No reason it should, and the amplitude didn't change. I still had 3 spots. So what do you think is what if you could see the waves, what is happening? Yes?
You get a phase shift?
Which phase? Where do you get a phase shift?
Sorry, what do you mean by that?
Pardon? A phase shift between what and what?
All the spots.
Very good. So what happens if phase changes? So if I could see that wave, when I move the grating, the 3 spots will be there, but the phase of the light will change, because the eye cannot see the phase, right? If I look at a laser pointer spot, if I shifted the phase of the light, it will look exactly the same. The eye can only see the amplitude. Okay? But if you could really see the phase, if you could see the waves coming out here, when I move the grating up and down, I would see the phase change. Okay, and actually this will change in an opposite direction than this. If I could see the phase, this one, here I have some green chalk. So if I did this experiment, let's erase all this, and originally a sine wave came out here, and a sine wave came out here, and this was a 0 order. If I move the grating and I could see the phase, I would see that this phase, say, is moving like this phase doesn't change, and this phase is moving the opposite direction. When this grating is moved up and down, like to this position. Okay? And this is something that very few people think of, because you don't see it. So all the people who do experiments with a grating, they can, until recently, it was difficult to really visualize or measure the phase. Actually, the only way to measure the phase is by interference, because the light is too fast. It's only today there are some more tricks you can actually see the phase other than interference. But certainly many years ago, you could only indirectly see the phase by interference. Okay, so that's why people didn't think of using this. But in the 1960s, 1970s, some people said, just a minute, if you can see the phase, you can make a different type of interferometer. You can take these 2 beams, you can put 2 mirrors here, which throw these 2 beams together. And now when you move the grating, then you get a bright and dark, because the phases will either add up constructively or destructively. So some physicists or some people said, if this is a grating, and if I have the laser, okay, and we already know the answer, there'll be 3 beams, okay, separated by an angle which you already know is lambda over d, and we already know that the phases will be changing. So if you put a mirror here, and I put a mirror here, I block this one I don't care, I just stop it. Now this mirror will return this beam, this mirror will return this beam. So here, if I put a photodetector, this is my detector, and I move the grating, these phases will change just like I drew before. This was the original phase. Let's say the original phase, as is set up now, will get constructive interference, because everything is symmetric, everything is equal, so the 2 waves will add up the way it's drawn. But now, if I start moving the grating, we said this phase will change one way, this phase will change the opposite. So at some position of the grating, there will be a half a wavelength shift, I'll get dark. So now this grating is connected to what I want to measure. This is my X. If I move the grating one line, which I can make as any size I want, okay? If I move it one line, this is going to change from light to dark back to light again, okay? So physicists noticed that, but nobody kind of realized what the significance of that is to building a sensor. They said, fine, it's another way. In a classic interferometer, you moved the mirror, and you didn't have a grating. In a classic, meaning Michelson interferometer, you move the mirror without a grating. Here you're moving the grating instead of the mirror. Okay, so what's the big deal? But there is a big deal. There is a big deal because this interferometer can run from an LED. It doesn't need a laser. So the big deal here, you can replace the laser. You can replace the laser with a simple LED, and the thing will still work. And that's a big deal. Now, can somebody explain why the classic interferometer has to have a perfect laser, and while this one will work with any light source, even a candle, or a light bulb, or an LED, and it'll still work as an interferometer. You'll still get light and dark bands, and you'll have all the advantages of an interferometer without needing a laser. So I'll give you a minute to think about it. So just to remind you, in a normal laser, in a normal interferometer, you needed a very stable light source, because after the light came back from a big distance, it still had to be in phase, and you changed the distance, and you wanted to change it and to see constructive and destructive interference. Okay? Yes?
Because maybe the light only needs to stay coherent until it hits the grating. After that, the information is summarized in the angle. Yes.
Not really. The angle doesn't change. When I move the grating, the angle doesn't change, and I explained it before, that the only thing which changes is the phase of the light. Nothing else changes. Okay, so let's go back to classic interferometer. If I change the wavelengths of the light in the classic interferometer has two passes for the light. Let's say, again, we'll make it simple again. We have one pass of the light, the way I drew it before, and we have another pass of the light, and we are changing the length of one pass by moving one mirror. So, if the difference in pass gives you some interference, but if the wavelength was different, the difference in pass will be a different number of wavelengths or a different phase. So let's say that the difference in pass here is, say, 300 nanometers for helium neon, for 633 nanometer. I'll get dark. But if I change its wavelength, say, from 633 to half of that, I'll get light, because the difference in pass will be a full wavelength. So what matters here actually is the delta x divided by lambda, and this tells me the phase shift. So this equals to the phase shift, and the phase shift determines if I'll get constructive or destructive interference. Because when you have a sine wave and you move it delta x, the phase shift is delta x over lambda times, of course, 360 degrees. But this is proportional. Let's make it proportional to the phase shift. So if I change lambda for the same difference, I can get a different phase shift. So this can only work at one lambda. Because, for example, if I had this wavelength and half the wavelengths, whatever is bright for one wavelength will be dark for the other. So it wouldn't work. Okay, so let's look at this. What's different here? Yes?
It doesn't need to have coherence because it comes from the end.
Almost. Yes?
The phase shift's the function of the diffraction gradient, not of your specific...
Almost. You're both very close, but there's something glaring at you here which is different from a normal interferometer. And the thing is, the path is always constant, because the path length, which is from here to here, from here to here for one beam, and for this from the other beam, regardless of the grating position, the path length, there is no delta x. The path length is always the same. Now, if the path length is always the same, if I take red light, green light, blue light, the interference will be the same. Because interference has only to do with the position of the grating. I'm not changing the path. So if I adjust it for the path length to be the same, and I put in red light, and I move the grating, at some position it will be dark, some position will be lit. If I change it to blue light, the angles will change, but path length will still be the same, okay? And the phase shift will depend on the grating position versus the beam. Path length stays the same. So if the path length stays the same, then whether I get a dark band or a light band will only depend on the grating position relative to the beam. In other words, I'm assuming the beam stays the same size. If the beam stays the same size, so what I'm drawing here is this. This is my beam, and these are the grating lines. Usually there are more, but let's say there are four grating lines in the beam. So, and the first one lines up with the beam. Okay? So I'm getting a certain phase shift in the two orders. If I move the grating from this position to this position, I get a phase shift. Now, if I change the color of the light, it doesn't matter, because the phase shift comes from the relative position of the lines in the beam, and not from the path length. Because as I explained before, this drawing that I drew before, where I get constructive and destructive interference, okay, this, if you redraw the beam, you'll get a different phase, but it doesn't depend on the wavelengths. Only the angle depends on the wavelengths, but because of symmetry, regardless of angle, as long as it's symmetric, the path length is always the same. So if the path length is always the same, if two red wavelengths end up interfering, two green wavelengths will also end up interfering because they'll come together. Let's say this path, let's say this path is 10 centimeter, and you divide it into red wavelengths, and you get a zillion wavelengths plus a half of a wavelength. But you get the same on both arms. Now you put in green light, you get 2 zillion plus a quarter wavelengths. But it doesn't matter, they'll still end up in the same phase. So when they end up in opposite phase, they always destructively interfere, okay? And if you change the wavelengths, okay, it will still end up the same. Because when these are exactly the same and the phase is the same, they'll always be constructively interfere. When the path is the same and the phase is different, the 180 will destructively interfere. And what determines the phase is the grating position. Everything else stays the same. It's always equal path. So if you have an equal path interferometer, it works with any wavelengths, and because of that, it can work even with white light. And this is called white light interferometer sometimes. It's also called grating interferometer, because it gets a phase shift from the grating. Meter. Okay? But what is more important here is to understand that any interferometer where the path length is always the same can work in white light. And this is actually the basis of a very clever instrument which we don't have time to discuss in this course, which is called a profilometer, which measures the 3D surface of an object by white light interferometry. But we don't have time to discuss it, but we do have time to discuss this. So this is a very good position sensor, because you can take this grating and make it very, very fine. And typically when you make a very fine grating with a traditional encoder, you have problems because you have to resolve the lines. Because Basically what I'm comparing this is to a linear encoder with the same fine grating where I want to read the line position directly. But if I want to read the line position directly with a microscope, the finer the lines, the harder to read. I have focus problems. Here I don't need to focus anything. If the light source moves, if this moves, it makes no difference. And I can make the lines so fine that I could barely resolve them even with a microscope, because the light will just average many lines and interfere. So I'm getting averaging, because the beam covers thousands of lines. I'm not looking at one line, I'm looking at thousands of lines. That's very important. I'm getting a very big averaging. I don't have any focus problems. Okay? So you have to remember that the lines in a grating can be much closer than a wavelength of light. Okay? So the grating I showed you before, the grating I showed you here, when I made the spots, the lines looked about like that. The lines seemed to come out from that grating at about 45 degrees. Okay? So when I plug this into the formula, if I say what is the pitch of the lines in the grating I showed you, so I say alpha, okay, was about 45 degrees, and again I have to express it in radians. So let's say 1 radian. Let's say it was about 1 radian. So 1 radian equals lambda over d. Okay, and I knew the lambda that I used is about 650 nanometer, so d was 650 nanometer. So the grating I just held here and showed you was about 650 nanometer line pitch. But you can get gratings which are like 100 nanometer line pitch. Okay, so it's very hard to read them directly, but this way you don't care, you don't have to focus on the lines. So now you can have an encoder which has thousands of lines per millimeter, but you don't have to see the lines, you don't have to resolve the lines. All that you're measuring is the phase shift they cause by interference. So this is a very powerful technique, and that's called a grating interferometer, and that is the basis of all the very high quality position sensors today. So in other words, this replaced the classic interferometer in many position sensors, because this can be made very compact, because it doesn't have a laser, it has an LED. It can be made very cheap. Okay? So these are available in units the size of a matchbox, and with resolution of 10 nanometers, say. So I'll bring in one on Thursday and we'll discuss it a bit more. But if you have the time, just look up a bit on interferometers on the internet and grating interferometers to see what they can do. Thank you.